Good morning everyone, and welcome to today's worked exam answer video. Today I'm taking a little bit of a break from the calculations, although they will be returning tomorrow. Another area that a student has requested from me is NMR, and walking through NMR questions and thinking about how to deal with all of the information that we might be given as we are in this table here, thinking about what all of these different peaks tell us about the structure, and then piecing all of those fragments together to come up with the final structure. And that's exactly what we've got to do here. First of all, we've got to work out the whole number integration ratio values, because they've not been given as whole numbers, so we're actually going to get a mark for that, which is quite nice. Then they've asked us to specifically think about two of the peaks from the table, the peaks at chemical shift values 3.5 and 2.2, and to explain what's going on with the splitting of those peaks. And then we have to deduce the structure of compound X. We don't have to explain how we've got to that structure, but that here is actually worth 2 marks. Because we haven't already identified all of the different fragments. We've only been asked to identify in the previous question sort of 2 of the fragments from the 5 peaks, and that's why this question is worth more than 1. Lots of students have said to me that they find it quite difficult once they've got all of the different fragments to put them all together. And I just want to start by reassuring everybody that that's usually only going to be worth 1 mark. I know this particular question is worth 2, but as I say, that's because to get the final structure of X, we still have to identify some of the fragments. So if you look at this table and you're able to identify using the data sheet and the integration values and the splitting patterns what these 5 fragments are, even if you can't put them all together to get that final structure, you will only be losing a maximum of 1 mark in the questions that I have seen to date. So with NMR, it might be that you feel that you're spending a long time on these questions, and perhaps a little bit too long of a time. My advice would be to allow yourself a few extra minutes compared to the number of marks that are available, but then be really disciplined and say, right, if I haven't got a structure by this point, I'm going to have to move on. And please move on in the knowledge that if you have got all of the different fragments, you will only be losing 1. I would say certainly never ever more than 2 marks in that question. It would be far worse, in my opinion, to realise that you've spent sort of an extra 5-6 minutes on this particular NMR question and not actually got an answer, and then that impacts the questions that follow. So my suggestion might be to be quite disciplined with that. Note the time which you start the question, set yourself a time limit for how long you're going to give to the question, regardless of whether you're finished or not at the end of that time, potentially moving on. So what I will do is I will annotate this table as I would normally annotate this table. And I would do that regardless of whether it's then going to ask me to explain parts of the table further down. I just like to get my head around exactly what all of this information is telling us, and I'm going to use different colours for each of the different peaks so that we can see, when I then put it all together down here, how all those different pieces link together. And obviously I will explain that as clearly as I can and as thoroughly as I can for you guys, but as always I would be very happy to take questions, and I will get back to those as soon as I can. Right, so let's try and go through this as systematically as I possibly can. So, regardless of whether this was the first question or not, if I'm ever presented with a table that contains integration values that are not whole numbers, the first thing I'm going to do is turn them into a whole number ratio. Now, the beautiful thing is we get a mark for doing it here. How have I gone from 0.6, 0.6, 0.6, 0.9, 0.9 to 2 to 2 to 2 to 3 to 3? There's a couple of different ways we can do this. Similar to when we're working out empirical formula, pick the smallest number and divide all of them by the smallest number. So 0.6 divided by itself would be 1, 1, 1. 0.9 divided by 0.6 would be 1 1/2 and 1 1/2. Then we could just double all those numbers to get the 2, 2, 2, 3, 3 ratio, which is obviously the whole number ratio that we're after. Alternatively, if the numbers are fairly nice like they are here, you might be able to recognise, oh, well, 0.3 goes into both 0.6 and 0.9, and then we can think about how many 0.3s go into 0.6, which is 2, and how many go into 0.9, which is 3. So that gives me 22233. Now this is really helpful because this tells me how many hydrogen atoms are in each environment. So in this red environment, there are 2, in the pink, there are 2, in the purple, there are 2, in the bluey grey, there are 3, and in the light blue, there are 3. That then comes in really useful when we're drawing the fragments, and I'll get onto that in a second. So that would always be my first step anyway. Then I would use the splitting patterns and add a row underneath that tells me, if that's the splitting pattern for that peak, how many hydrogens need to be in the neighbouring environment. And we use the n+1 rule, where n is the number of neighbouring hydrogens, we add 1, and that gives us the splitting pattern. So for a triplet, there needs to be 2 neighbouring hydrogens, because 2 + 1 gives me 3, which will give us a triplet peak. For a quartet, that's going to need to be next to 3 hydrogens, so 2 + 1 is 4. Triplet, again, 2 hydrogens. Singlet is going to be next to no hydrogen, so there has to be a break in the chain somehow, which can be done in a multitude of ways. The chemical shift value will help us to see what kind of break in the chain that is. So no neighbouring hydrogens plus 1 gives us a singlet. And then again, for the final triplet, that's again going to need to be next to 2 hydrogens. So I'd always annotate that one as well. And then the final thing that I would do is look at the chemical shift values and go to my data sheet and have table B in front of me and go, okay, so if we have a peak at 1.1, that's going to be a CH3 group. And again, like I said, this is where the integration values come in really useful, because we know we've got 3 hydrogens in that environment, so it's definitely going to therefore be a CH3. If we only have 2 hydrogens in the environment, make sure you only draw 2 and then you leave a space, because again, that's going to really help you when it comes to piecing together the puzzle. So on the data sheet, for this peak here, for example, they would only draw 1 hydrogen in the bold on the carbon next to the C double bond O. Now that doesn't mean that there can only be 1 hydrogen there. That's basically saying there is a minimum of 1 hydrogen on that carbon. We know that there's 2, so draw 2, because then you know that you've only got to fit something in on the end bond that is missing a hydrogen at this point. And that applies to every single peak. Now, the next question asked us to do this specifically for the peaks at 3.5 and 2.2. So I've done these down here, but if we weren't asked for that, and I had a bit more room around my table, I would have just done the same thing that I've done up here for these 2 peaks as well. So literally just looking on the data sheet and looking at where those chemical shift values lie. Now occasionally you might have a chemical shift value that looks like it's going to fall into more than one range. At this point, it's a good idea to check the molecular formula, which we were given, C6H12O2, because if it's suggesting that it could be a hydrogen on a carbon with a halogen, well actually no, it can't, because there's no halogens here. Or if it's suggesting to you that you've got a hydrogen on a nitrogen, well, not here we don't, because the molecular formula doesn't tell us that. So the molecular formula is also useful, and if you're given infrared information, that's also useful because it might tell you what functional groups you have. We haven't got any of that, but we're still able to put the structure together because hydrogen NMR on its own is very, very, very useful. So in order to actually answer the next part of the question, which says to use the data in the table above and table B in the data booklet to deduce the part of the structure of X that causes the signal at chemical shift 3.5 and the part of the structure of X that causes the signal at chemical shift value of 2.2, and we also have to explain the splitting patterns of those peaks. Well, we've already kind of done that in our annotations within the table. So for 2.2, looking on our data sheet, between 2.1 and 2.6, we have hydrogens on a carbon adjacent to a C double bond O. Now, at 2.2, we figured out that the integration value was 3. So again, on the carbon adjacent to the C double bond O, I've drawn 3 hydrogens. That tells me that this has to be one end of my structure, because I can't draw anything to the right of that CH3 group. So that is going to be one of my ends. Very helpful. Now in the table it says that this is a singlet peak, so I've explained that by saying that a singlet peak means there are no neighbouring hydrogen atoms, and of course there can't be, because next door you've got a C double bond O. There can be no hydrogens on there unless the R was a hydrogen, which again it can't be, because that would be suggesting that that was then our final structure, which it's not, because it has to have 6 carbons, 12 hydrogens and 2 oxygens. So that's the 2.2 peak. And then for the peak at 3.5, doing exactly the same thing, we've got a carbon adjacent to a single bonded oxygen, and because there's 2 hydrogens in the environment, I've drawn 2 and then left that blank space there. Because it's a quartet, that tells me that there are 3 neighbouring hydrogen atoms, which means to the right of here, we have to have a carbon that's bonded to 3 hydrogens. We can't have neighbouring hydrogens to the left because we've got a singly bonded oxygen. So that immediately tells me that there's going to need to be a CH3 here. Oh look, we have a CH3 fragment in the blue. That's got 3 hydrogens in the environment and it's a triplet peak, so it needs to be next to 2. The pink. And this is where it all starts to piece together. So then, using the colours, I've pieced all of those 5 fragments together. Now, I appreciate what some students struggle with is thinking about flipping this round, so I've now drawn that with the CH3, then the C double bond O there. And I could have drawn that on the right hand side and done this whole structure the other way. I guess the data sheet will always present them in a certain way and you might need to flip some of the fragments around. The other thing that I know students find difficult is we've got 2 peaks that lie within the 2.1 to 2.6 range, and the 2.2 peak, as described, is a C double bond O next to the CH3, and that forms one end. But then we also have this peak here at a chemical shift value of 2.6, which again suggests a carbon adjacent to a C double bond O that has 2 hydrogens on it. And some students will be thinking that that means that there's 2 C double bond O groups. Now, I'm not saying that there can't be, but because we've also identified a single bonded oxygen to a carbon, and we know the molecular formula only contains 2 oxygens, there can't be 2 C double bond O's, because that would then give us 3 oxygens in total. And of course, we can have, if we've got a ketone, a carbon either side of the C double bond O. And that's what I've tried to show really unclearly here. My apologies for the colours, but I've shown that the C double bond O is the C double bond O in the deep bluey grey colour, but it's also the C double bond O of the lilac fragment at the top there. That's the same C double bond O, we just have a carbon on either side, which has hydrogens on. So that dictated that they had to go there, and then the lilac peak has 2 hydrogens in the neighbouring environment because it's a triplet, and the only 2 peaks that we haven't yet, the 3 peaks that we haven't drawn, the red, the pink and the blue, well, we've already established that the blue and the pink are going to go together. The pink then has this single bond O, the red has a single bond O and 2 hydrogens on it. So that would suggest that the red peak is going to be next to the purple peak, both triplets, both next to 2 hydrogens, which they are if I put them back to back like that. Then again, we've got 1 singly bonded oxygen. We have the red peak at one side and we have the pink peak at the other, and that is the same single bond O. Again, if I had 2 separate single bond O's, I'd need more oxygens in my molecular formula, and I just don't have that. Then, as already discussed, put the blue peak next to the pink peak so that the blue peak, with our 3 hydrogens in its environment, being next to 2 hydrogens to make it a triplet, that is matched there. And I would always, whenever you've put your structure together, check a few things. Check it matches with your molecular formula. It does. I counted. I've got 6 carbons, 12 hydrogens and 2 oxygens, which is great. Check that you've got the right integration ratios for each of your peaks. So that should be 3. The lilac should be 2. The red should be 2. The pink should be 2. And the blue should be 3. Fab. Check that the splitting patterns work. Singlet, yes. Triplet, yes. Triplet, yes. Quartet, yes. Triplet, yes. And if you've got other information like your infrared functional groups that need to be present, check you've got those in there. If you've got carbon NMR data, check that it all matches up with that as well. And then when it does, you can be happy you've got the structure correct. Fabulous. If you are struggling to think about how to put these fragments together, my advice is to just try something. Because I feel like, again, with NMR, you could draw the 5 fragments out and then sit there for a very long time looking at them and not really seeing how they go together. If you try and put them together, you'll likely get to a point where you go, oh, it can't look like that because of this. Or if you think you've put together a structure that might work, then again, compare it to the data. If it works with the data, you've probably got it right. If it doesn't work with the data, then hopefully you'll be able to see why it doesn't work and then know how to make a change. Whereas if you don't commit something down to the paper and you're just trying to visualize it in your head, I think that's a far harder way of seeing how the fragments may link together or how they may not link together. So don't be scared to commit something to paper, even if you do it in pencil and you rub it out, or, you know, do it in pen and cross through it. Just don't use up all your available space. But that would be my advice again with NMR. And in order to get quicker at these and more proficient, practice. Because then you're going to start to see some of the little tricks of NMR in terms of which peaks might be next to each other, in terms of seeing the same sort of patterns and the same sorts of chemical shift values and everything like that coming up question after question. So that would be my advice as well for NMR. Hopefully that's not been too overwhelming. Hopefully I've been able to explain that and my thought processes and how I came to put it all together as clearly as I can. If, as I said, there are any questions at all, please do not hesitate to get in touch. Or if you're attempting a different NMR question and you get to the point where you get a bit stuck, again, let me know and I can help you to see whether what you've done so far is correct and kind of how to progress on to the next part of the question. Thanks so much for watching, guys. Wishing you all a really lovely day.